So this will be number 4. We've done 3 on mastering regression RStudio. There's the 3 of them, so this will be number 4. And maybe for now, I think maybe the last one. We'll see if we have sufficient time. If we ran out of time, I'll do a number 5 for now. But I think we can almost probably stop here, and I want to switch to something else. I'll come back to it. It's not that we will forever and ever not come back, but we'll see how it goes. Okay, so remember the previous video, episode 3, we basically ran our regression and then performed a whole lot of tests. And remember, it's all about those coefficients. All about those coefficients. We want to determine how accurate, how reliable, how robust those coefficients are. And that's really why we perform all these tests. We want to, with some degree of certainty, confirm or be satisfied that those coefficients actually are what those coefficients are. Okay, so I'm going to, for this particular video, run through these tests just as a summary, because I do think they are very, very important. Okay, so if you can remember, we're going to open RStudio. So I've opened it, remember. I haven't done anything, as you can see. I'll just open it now, literally 5 minutes ago. Okay, so I'm not going to, we don't have to install packages now the whole time. As I said, I normally do that maybe once in a quarter. It's now and again good to run it because there's updates. Okay, they do update these packages, but it's not like it happens every week. So I'll run it about once a quarter. Normally, when I upgrade my RStudio versions, I normally upgrade these ones as well. But what I do have to do, what I must do, is load these libraries again. Okay, I have to load these libraries. Okay, I have to load them. If I don't load them, I might have problems. Okay, so I just highlight them all. Okay, just highlight them all. You don't have to do it one by one by one by one, and just run it. Okay, and remember, as what I normally do, I run it a second time just to make sure they're all blue. I can run it a third time, a fourth time, but normally by the second time it's sorted. Okay, now, when we left off yesterday, I didn't make any changes. So I'm not going to run them one by one by one. I'm just going to highlight them all. Basically up to here. You can do more if you want to. But up to this point, it's basically loading the data, checking the data, creating the variables, like a date variable, then abbreviating my variables, stating my variables, calculating certain variations of the variables, plotting them, etc. So you don't have to do these things now one by one by one. I just highlight them all and I just run it. Just for safety, I'm not interested really in any of the output. I just want to make sure that all my data is now loaded, it's declared, all the important stuff that I wanted to do is done. And then I just go straight through where I left off. Okay, I just go straight through, sorry, where I left off. Okay, and that is my equation. So I run my equation and I put the summary. Normally I just do these two together. I run it, and there's a summary. Remember still the coefficients. Okay, and it's really, as I said, it's all about those coefficients. It's all about those coefficients. How accurate, how reliable are those coefficients? And that's why we perform all these tests. So all these tests is about that. Remember, we test whether they're 0 or not whether they're minus 3.38, just whether they're 0 or not. So that test is satisfied. And then we do all these other tests that we've gone through. And within the script, there are they all. Okay, there's a Jacques-Boara test, a Shapiro test, Durbin-Watson test, BP test, heteroscedasticity, the reset test, the WIF test, the correlation test, the Ellis-Collin dialogue test, etc. There's more, but these for me is the important ones. Okay, these for me are the important ones. And as I said, they all focus on predominantly on the error term, the error term. Remember, the error term is the difference between our estimate, our actual, and our estimate. Okay, so most of these tests focus on the error term, this error term here, which is simply just the actual minus the y hat, which is the estimate. Remember, I went through in Excel and I show you how we can calculate the estimate, and then from the estimate, we can then generate the error term. Remember, this is what is not explained within the model itself. Just remember, this y is the constant and the coefficients. And we want to minimize this error term, and that's important. And so all these coefficients that we're focusing on, all of them are focused on the error term, because these coefficients, okay, by using this coefficient, we derive the error term. So these coefficients influences the error term. Anyway, these are all in the previous video tutorial. Go and have a look at it. Okay, so let's have a look at what do we do first. We run the Jack-Boara test. We did that, but let's run it. Okay, so let's run them all. Okay, I highlight them and let's run them all. Okay, so let's go up and start from the bottom. There's the Jack-Boara test. There's our outcome. Okay, there's our outcome. So let's have a look at the Jack-Boara test. The Jack-Boara test. Okay, purpose: whether the residuals are normally distributed based on their skewness and kurtosis. Now remember skewness and kurtosis. So skewness, if I can draw that quickly, where's my pen? Skewness is either a positive skewed or a negative skewed. Okay. Positive skew, lot of small numbers, few high numbers. Negative skew, lots of high numbers, few small numbers. Okay, so this is typically the rain participation. Most days there's very little rain, and a couple of days where there's a lot of rain. So that's skewness, and kurtosis is whether it's really about whether it is steep or whether it is flat. Okay, because remember, ideally we want a nice looking bell shape. Okay, so skewness and kurtosis is a deviation from this bell shape, and therefore it doesn't follow a normal distribution. Normality is important for our levels of significance, because in our normal distribution we assume that 95 is there, 98% is there, and 1% is there. Okay, so here our mean is there. So you can see there that doesn't represent the exact same number. So this is implications for the level of significance. So what may happen is we may, for example here, if we run the F test, where's the one? Okay, now, so let's say this was close to 0.05. So let's say that value, that p-value was 0.058. Okay, then we'll reject the alternative. We will accept the null hypothesis that value is 0. However, that value is actually wrong, and therefore we will reject the statistical level of statistical significance for wind. However, we should have accepted it, and that's the importance of residuals being normally distributed. Now, for example, something like this, where it's so small that it doesn't really matter, it's not an issue. But when you're on the margins, between accepting and rejecting, then this becomes important. So you might accept where you should have rejected, or you will reject where you should have accepted. So that's where normality becomes important. Okay, residuals are not normally, so here the P failed to reject, residuals are approximately normal. So that's important. So in this case, we want to accept the null hypothesis. Okay, so that's what we want. We want to accept the null hypothesis. And to accept it, it must be bigger than 0.05. Now, it could be 0.01, it could be 0.1, depends whether we're working on 95, 1%, or 10%. But in typical fashion, we work with 95%, i.e. p 0.05. It doesn't have to be that way. For example, it could be 0.01, it could be 0.01, it could be 0, or it could be 10%. So that's 10%, 5%, 1%, 1/10 of a percent. Okay. Now, typically, I said we do it roughly there, and that's a t-value of approximately 2. Okay, so we assume, except if otherwise stated, we normally work within that specific parameters. Okay. Okay, so let's continue. So that's the Jack-Bowara test for normality. Okay, hope that makes sense and why that's important. And obviously, same for the Shapiro test. Obviously, the same for the Shapiro test. Let me just quickly get there. Again, we want a p-value of higher than 0.05 because we want to accept the null hypothesis. Shapiro test is more powerful for smaller groups, while Jack-Bowara is often preferred for larger groups. So I just normally run both of them because, as I said, they do complement one another. It's only in certain instances where they will contradict. 90% of the time they will support one another. They will complement one another. It's only in the margins where they will, and then it becomes a, let me put it this way, your choice, eeny, meeny, miny, mo type of thing. Okay, so that is the Jack-Bowara test. Now, as I said, it's, let me just save here, it's really about the distribution of my error term, the distribution of these unobserved variables. And the impact is, if it's not normally distributed, you might accept or reject the null hypothesis where you should have rejected and accepted the null hypothesis. Okay, but as I said, that's basically on the margins. Okay, so that's the test for normality. That's normally first one. As I said, important to test. Then this is where it becomes critical. Okay, this is where it becomes critical. It's the autocorrelation test. Now, we don't want your data to be correlated. Okay, don't want your data, because then your coefficients are wrong. So if your data are serially correlated and that minus 3.8, then these coefficients are wrong. Okay, they're either significantly understated or they're significantly overstated. Okay, so it's very important that we test for it. There's some, we can put some visualizations to the autocorrelation. So for example, we can we see there's the normality plots there. I'm not going to do that. I want to look at the want to do a, what do you call this now? You can do a autocorrelation function. Let's see if we can do an autocorrelation function and partial autocorrelation function with this errors. So let's quickly see, where can I put it in? Let's see if I can put it in there. And so to visually present this, let's see if we can do LMS. I'm not sure if it's going to work. Let's try. I should have done that. Let's see if we can. I'm sorry, it should. Let's do this LMS at the residual. Let's do that, because LMS, that is just the equation. I want the residuals. Let's see if we can do that. There we go. So we can do that. So there's the autocorrelation function and partial autocorrelation function. I'm not going to go into the details, but this visualizes correlation, autocorrelation in the residuals. Let's have a look here. So normally when it's got this, it means that there's significant correlation. And you see there's your there's your level of significance. So ideally you want all these spikes to be within this level. But you can clearly see there's a high degree of autocorrelation between the numbers, which is this one. Remember, correlation is between, in this case, between 0 and 1. So in this case, it's going to be almost, so basically today and tomorrow are highly correlated. If today is 10 millimeters, tomorrow will be 10 millimeters. So this is significantly correlated. And you see here as well, it indicates strong correlation. Specifically, you can see in a, because this is period 12. So this suggests a high degree of correlation on a seasonal level, meaning January to January, February to February, March to March. You can see in between, from March to April, April to May, there's nothing. Okay. But you can see monthly, and this is again, here's monthly. So there's definitely some serious monthly correlation going on here. So you can see that although in the test, where is it now? In the test, you'll see it doesn't indicate, sorry, where is it now? Durbin-Watson test, it doesn't suggest autocorrelation because it is values greater than 0. Now let's have a look at the Durbin-Watson test. What is the null hypothesis? Residuals are not correlated. Errors are independent, meaning they are random. Okay, they are random. 10 is not 10, is not 10, is not 10. It's 10, then 200, then minus 6, then 3/4. It's all random. Okay. So in this case, we have a p-value bigger than 0.05, and therefore we're accepting the null hypothesis of no autocorrelation. However, and this becomes now the point, is I'm concerned about that value, the p-value of 0.05. If you look at the autocorrelation graphically presented, and if you look at the error term not normally distributed, I think that p-value is not correct. So in this case, it's exactly what I said now. We're now accepting the null hypothesis, whereas we actually should reject the null hypothesis because of the errors that are not normally distributed, the error term that are not normally distributed, the residuals that are not normally distributed. So here I've got a question. So although on the margin it suggests that there's no autocorrelation, in the error term, I'm not too sure that that's actually true, and this is disputed. So we'll have to do some further digging in that. Visually, it suggests there's autocorrelation. The error terms not being normally distributed suggests that this p-value is incorrect. And so here we are accepting the null, where I think we should actually reject the null because it's on the margins. You can see it's very, very close to 0.05. So this is a question mark. Okay, the data suggests, as it stands here, that there's no autocorrelation, but I said I have my doubts and I can justify why I have my doubts. Okay, so that's important. So, but anyway, this is important to understand, is this idea of residuals being correlated or not correlated. We want the residuals to be totally independent. We don't want it to be correlated, meaning 10, 10, 10, 10, 10, 10, 10, because what's the point of the model? If all the values are the same, if we know the value is 10 and we know they are serially correlated, then we know that it's going to be 10, 10, 10, 10, 10. And therefore the coefficient will be calibrated to predict a 10, 10, 10, 10, 10. And we know that real life things are random, not 10, 10, 10, 10, 10. So we need to make sure that there's no autocorrelation, serial correlation in the errors. And I said, although it is, it's not, meaning we failed to reject. There's no evidence of zero correlation. I am concerned. Okay, but yeah, it's a very, very important test statistic. Very, very important test statistic. And as I said, we can also visually present it by using the autocorrelation function and the partial autocorrelation function. And I said within these two functions, we want all these spikes to be within this 5%, because this is the 5% in the blue, and you clearly see it's not. And so this, if you look at the autocorrelation function that looks like this, it typically suggests serial correlation in the errors, and that's evident here. So visually, it suggests autocorrelation or serial correlation in the errors. The test doesn't suggest it, so we have a conflict of interest. Which one do I believe? I don't believe this test to be true. I believe this test to be false because of the non-normality of the errors. So I believe rather that there is, rather than there is not. But that's a judgment call, and you have to be able to substantiate why you say this or why you say that. You can't just take it. You can't just take it for granted. You have to interrogate also these. If it's under the margins, if it was like 10, p-value of 10, fine. So you have to test these things on the margins to make sure you actually can be able to don't just blindly believe. You can visualize it, you can cross-correlate it, but just check. Okay, so that's important, and that's a good case study. So what's our next one? Our next one is the heteroscedasticity or homoscedasticity. Residuals have zero variance. So let's have a look at that one. So there's homoscedasticity, constant variance. We use the Bruce-Pagan test. And here we also want, oops, sorry, let me go to pins. Here we also want the null hypothesis, okay, which is the errors are constant variance, meaning our model is able to predict not just the average numbers, but also the outlier numbers and stuff. Okay, so we want to accept the null hypothesis. In this case, Sandel-Bruce-Pagan test is very, very small. So therefore, in this case, we are not accepting the null hypothesis. We are accepting the alternative hypothesis because our errors are so small, this one here. So that means model might need transformation or robust standard errors. Okay, that implies that our coefficients are not able to accurately predict the outliers, etc., etc. And I've showed you that in the graph in the previous video. I showed you the model, the predicted. You can clearly see the predicted values are on the margins, on the averages, but it can't predict the rainy seasons. It's impossible to predict periods of high rainfall. Okay. So that is another important test. And then we look at the reset test now, the omitted variable test. Now this is again very important. And again, if we look at the results, we can see that 0.4836, very, very small. So the model can only accurately account for about 48% of the variance in the dependent variable. So 52% plus minus unobserved, undeclared is in the error term, is in the residuals, which is unacceptably low. So we need to get that number up. So we test for omitted variables just to make sure, because we've got this hunch, we've got this hypothesis, we test it. And here we also want to get the null hypothesis. We also want the null hypothesis. Let's have a look at our results. Reset, again, very, very, very small p. So in this case, again, we failed to accept the null hypothesis We fail to accept the null hypothesis. We reject the alternative hypothesis, which means the puzzle is misspecification. Okay, we must consider adding quadratic terms or interactions or trends or other variables. Okay, we need to find variables that can account for that 52%. We need variables that can account for that 52%. Just by the way, when we look at homoscedasticity, okay, when we say need transformation, we normally talk about logs. We normally log our data. That helps a lot with homoscedasticity, with our constant variance. So when we talk about transformation, we normally talk about logging the data. And therefore, I spent some time on logging the data. Let's quickly, just for interest sake, if we say, not lof, let's quickly look log R. Log max and log W. Let's see if I can just run. Let's see the summary output. There it is. You can see now it makes quite a big difference. Now all of a sudden wind becomes statistically significant, and they're both in and they're both negative signs, which I would expect it. So this looks immensely better by logging the data. If you remember, these are now elasticities. They're now elasticities. And they log format coefficients. So this is not coefficients in level terms. These are now coefficients in log terms. And maybe this could be our next video, is to talk about the logarithm log format of it. But let's quickly check for our homoscedasticity. Okay, so let's quickly run that. It's still small. It's still small. Student push test. So it doesn't really solve the test. Let's quickly run normality test. It doesn't really make a big difference. Our output is still, let's quickly run that one. So it's even better than that sheer correlation. So there's some improvement, but not much. Anyway, let's leave this, but you'll see it's still, R square is still very small, 48%, etc. So all that really happened is that wind became now statistically significant. But you can see, yeah, no, that's fine, 0.050, the sign. So it does improve, although the tests are still pretty much what it is. Anyway, let's leave it for now. But that is something that we potentially can do, is add all our results, put our formula equation in data in log format and run our equation in log format and see whether that solves some of the problems. In general, that's our standard practice, is just log it if you can. If you can log your data, it does really help. And you can see it does make some improvement in the data. But we can do that maybe as in the next video tutorial. We can maybe do that. Anyway, let's go back to, before we run that, let's go through. So we've done Durban boost. We've done a reset. Okay, so there's the reset test. The reset test is significant. Okay, so let's have a look at what's a reset test. Reset test, again, we're not accepting the null hypothesis. We're rejecting the null hypothesis. We're accepting the alternative. It says there's missing variables or non-linearities. Now, non-linearities is, for example, if we deal, for example, in population, then we cannot use a linear function to model population, because we know population grow exponentially. So therefore, we have to bring an exponent into our equation. Rain is not, rain is most probably linear, not exponential. Okay, so for linear, we most probably are not going to work with non-linearities. For example, power functions, the power of 2 or quadratic. although quadratic might work because quadratic goes up and down, quadratic could potentially simulate the seasonality. So that potentially can, but it's not quadratic. So again, we can add power functions to it, or we can just add variables if you have them. Okay, so that's important. Then the multicollinearity. Now that's another important thing. I said VIF equal to 1, no multi, VIF between 1 and 5, moderate correlation, up to 10, high multi-correlation. So let's quickly have a look at that. So where's the VIF test? There's 1.5, 1.5. So there's moderate collinearity between the two variables, which is maximum temperatures and wind. So this is when we include, and I spent some time on it and the video yesterday, is when we include, let's say, weekly and monthly in the same equation. They're basically the same thing. So both those coefficients will be wrong because they will take from one another, so to speak. Where it should have been 5, and it's now, let's say, 3 and 2. Okay? So the coefficients by themselves are wrong because they take from one another. It's actually the same thing. Okay, so we need to make sure there's no multicollinearity in our independent variables. So normally we run a regression, a correlation for the independent variables to make sure there's no dependence that variables that have high correlation with one another. We can use the VIF test in this case. It falls there, so there's some moderate correlation. So it's not like it's the end of the world, but it potentially has problems. Okay, potentially has problems. So you can drop one, combine them, applying dimensional. So there's some options, but if you have weekly or monthly, just drop one. Okay, because by dropping one, that coefficient will be incorporated in the remaining variable that was correlated. And we can use also just a normal correlation. That's normally what we run. A normal correlation, which is in this case 0.58, which is moderate, but it's on the higher side. So I would definitely, there's a correlation. I would definitely be concerned about those two. Although the VIF suggests it's not too bad, it's moderate, the actual correlation coefficient between the two for me is unacceptable. That's 0.6 basically, which is too high. Should be close to 0, maybe 0.1, maximum 0.3. This is too high. So I think the VIF is understating the thing. I think we'll definitely have to leave one of them. Okay, I would definitely have to leave it. Let's see if we've locked them. What does it do? What does it do if we lock them? Should still be the same. It should still be the same if we lock them. Yeah, still should be the same if we lock them. So yeah, I would just delete them. One of them, I think, because temperatures, the higher the temperatures, the higher the wind. The lower the temperatures, the lower the wind. So the two is actually very, very highly correlated. It makes sense because they're the same. It's not the same thing, but they within they behave very similar. If you put them on a graph, let's see where. There we go. Let's say I'm just going to make that 2. So there's temperatures, and if you put them on a graph, we can't. Let's see if I've got, there we go. Let's see if I can do this. This is better. Zoom. It's not very good in putting it in this way. But they're very similar. They behave very similar because, as I said, okay, so you have to understand the climate within my region of interest, meaning the West Coast. It rains in the winter. What happens in the winter? The wind is, well, let's quickly do this. Let's quickly do this, just as a means of running this. Have a look there. So this is summer. Temperatures are high. See, temperatures are high in summer, and then it becomes lower in winter. See there, 18. When is the wind the highest? The wind is the highest in summer, and it becomes less in winter. Okay. When does it rain the most? In winter. Okay, so you can see that temperatures and wind speed behave very similar, which is opposite to rain. So therefore, does we really need to add temperatures and wind speed in our equation? Because it does look to me, if you just look at the graphs, you look at it, they're highly correlated, they're the same thing. So no, we don't have to do that. And that was probably why in the linear, without the logs, it's not statistically significant. We can exclude it. And again, when we excluded it, you could see that it doesn't influence the outcome of the regression as such, in that the adjusted R square is still the same. So wind contributes almost nothing. Okay. And then, so that's the correlation. So again, we want the correlation to be close to 0. In this case, it is there. So again, we're going to say this is not good because it's closer to this one. Self pairwise multi before regression. Okay, so that's problematic. And then we could give the collinarity diagnostics, tolerance, possible multi-collinarity condition, strong collinarity. So let's have a look there. Where is that? The results. There it is. There's the index is 13 and 15. That's my index values. Let's have a look and see. Tolerance, condition index bigger than 30, strong collinarity, tolerance, possible multi-collinarity. It's key interpretation. So you've got tolerance, condition, eigenvalence, variance. Key helps confirm predictive variables are linearly dependent. From the results, you see that value is there. It is 13 and 15. It does suggest that there's collinarity. Okay, not significant collinarity by the statistics. But as I said, from I would take it out. Although it just says moderate, I would still not include both of them. But yeah, so that's the the test that we perform. And I said the test, there's just a little table to summarize all these tests. There's the assumption. Remember, these assumptions are blue. Let's put this item. These assumptions are blue. Best linear unbiased estimator. And that is focused on the coefficients. Okay, so we want to make sure our coefficients are best linear unbiased estimator. Okay, so as I said, and I'll keep on repeating, our focus is on these coefficients. Try to get an understanding of how reliable, how robust these coefficients are. We can test for robustness after coefficients. We haven't done that. So that's when we create subsamples in our data, and we run regressions for those subsamples, so smaller samples over different periods. And we get those coefficients, and we compare it with the coefficient for the entire sample, and it should be very close. So we can do a robust test of it, and. Okay, so there's a little table that sort of just summarize all these tests and what we're assuming. So this is important. These are all the assumptions that we're making. And these assumptions focus on blue, meaning to ensure, to test, or to speak to our primary assumption that our coefficients are blue, meaning our coefficients are the best linear unbiased estimator. And that's quite important. If we don't meet it, then we cannot with any confidence interpret these coefficients, meaning our coefficients are wrong. They are rubbish. They are useless. And therefore, if we start all over, we have to redo our equation. You cannot accept these coefficients as true or accurate or reliable if we violate all these assumptions. And that's very, very important. Okay, so here are a menu of tests that we perform. As I said, there's much more exhaustive tests that we can perform, but this is a menu of basic tests that we perform. As I said, our model sadly fails all of them. It fails all of these tests, and therefore, even if the my coefficients are statistically significant, just means that not zero. The model cannot accurately estimate those coefficients. Those coefficients are biased, etc., etc. In fact, they should not be statistically significant at all. They should be actually zero. So this is what these tests are all about. So as I said, visually we can present the test, statistically we can present the test. What is important for you is to understand each of these tests, what these tests measures, to what assumption it relates to, the hypothesis of each test, the level of significance of these tests, and the interpretation of these tests. And as a general, as I said, then to sum up is that this model basically fails all the tests. Each and every single one of them, it handsomely fails. What else can you say about it? Nothing much. So we go back to the drawing board. So we go back to the drawing board and say, okay, what do I do now? What do I do now? Do I stop, walk away, forget about it? Which is obviously an option. It's doing something else. Because remember, you can only do so much. Huh? You can only do things that's in your data set. So we can walk away. We can say, so be it. That's it. Or you can think about it. And again, if you look at the West Coast, when does it rain? It rains mostly in the night. So is maximum temperatures the right one? Let's try minimum temperatures. And let's keep it with wind. Let's keep it with wind and see what happens now. So let's run it now and see whether anything else happens. So it's minus 3.3. You can see the intercept is different. That's different. And now this is also very, very different. And all of a sudden it's statistically significant. Not at the 5%, so again on the margins. Problem is my R squared has just collapsed. Now it's only 35%. So it's not really making things better. But let's run these tests and see what happens. Because remember, we cannot just use this set of results. We have to go a bit deeper. We have to go a little bit deeper. Still not normally distributed. Not normally distributed. Durban test. Okay, this is better. Break and push. Nope. Fail, fail. It's a little bit better, but it's still a fail, still a fail, still a fail. So replacing minimum temperatures, with maximum temperatures with minimum temperatures doesn't cut it as well. So let's go back to maximum temperatures. Problem is, I think this wind speed, but the problem is I don't have many other options to do. So let's try the difference in temperatures, because when the difference becomes smaller, it rains. So let's try that one. Okay, I'm going to keep with wind for now, but what did I declare that difference to? Temp. I'll use temp. Okay, so let's see if temp works. So let's play around with temp, see whether that makes anything better. So let's write temp and run it again. Ooh, look at that. Look at that. Look at that. Look at that, boys and girls. Look at my R squared. 70%. Look at wind. I still don't think the sign must be positive, but look at that, it's 5%. Okay. Now, this looks optimistic. Let's run the tests and let's see what happens now. Let's see what happens now. Jack Powara, still that. Durban Watson, is that. So the results are pretty much the same. Still pretty much the same. So from the results, it's still pretty much the same. It misses something. There's something that it misses. Because adding variations in the temperature doesn't fundamentally change anything. Well, except the initial output. But let's say if we log this. Let's see if we log this. Let's see if we log this. And if I log that. Now, I don't think temp is going to log. Let's see if it logs it. I don't think it's going to happen. Yeah, it does. Okay, so there's no difference. Okay. Nope, 5.8. That becomes worse, although I like these coefficients. Let's run it. I don't think it's going to make major changes because we still fundamentally work with this. So, yep, doesn't work. You see 5.8. Nope, 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 nope. It doesn't make a significant difference because we're fundamentally still working with the same. Although I do think temp is a better variable to use than maximum temperatures and minimum temperatures. Okay, so let's take the wind out, the logs out. The problem is, okay, let's run it again quickly. I mean, adding that temp is basically what makes it. If I exclude wind, then let's exclude wind quickly. 68%. It's 68%. Sorry, where is it? Ah, come on. Damn, Thomas. 68. So that wind makes almost no influence. Okay, so most of these tests are going to be wrong because we only have one. Nope, still problematic. There's a variable that we're missing. It's not wind. Plus. You see, the problem is I don't have anything else. Because max, log max, min, temp, they're all the same thing. Wind speed is the only other variable. Palmer and soil moisture is not going to influence, but the soil moisture it cannot influence soil participation. It doesn't rain because the soil is wet. The soil is wet because it rains. So that doesn't going to work. So I don't have anything else that I can add here. That's a problem I have. So there's no data in my data set that I can add here, except some variation of temperatures and wind speed. So there's something that I'm missing here. So I must either add an exponent of one of these two or a quadratic of one of these two. Which, why would I want to do this? Because rain, let's put rain, lag, rain, comma, one period lag of rain 1 period. Oops, sorry, that comma, plus. Then let's see what that makes. Now, I'll tell you what I'm doing now. Nope. The adjusted R square is perfect. You see 100%. There's lag. So this is So what I'm basically saying that yesterday's rain is equal to today's rain. So I'm basically saying rain predicts itself, which obviously is rubbish. So I made it a dynamic. You can do that, but in this case, it doesn't work because you can see all the other variables. Obviously, these variables are already included in that, so it's not going to work. It's not going to work. Oh, it's -1, so I'll put 1 there. Sorry, put -1. Sorry, because I want to say there's something wrong there. It's still the same. Lag of rain, 1 period rain. So let's make it 12 periods. And that's just to cover seasonality. Still the same. It's still exactly the same. I've declared it correctly. Yep. So that's not going to work. Anyway, so I'm running out of options here. So I need to do things now. As I said, I either walk away and say, sorry, there's nothing much more I can do. I've reached my limit. I don't have the data. Or I need to go and look around to expand my data set. To go and expand my data set, find other data, cloud cover data, or atmospheric pressure data, or whatever data I need to go and find that can basically, and we know low pressures, high pressures, there's all sorts of other things that potentially can influence rain. So I need to find the data, bring it in. Otherwise, I must walk away because this is not going to work. Although we already know. No, it's the difference in temperature that actually are the important thing, a variable for rain, rather than the absolute maximum or minimum temperature. So that's already a clue that is worth quite a lot. Anyway, let me park there for now. So there's a lot of options that we need to explore. There's a lot of interesting things that we need to explore. So let's park that for the next video. I think that's important. So remember to save. And yeah, I hope you've enjoyed it. And with that said, I'll see you on the other side.